Okay, so in this video, I'm going to take a look at a few things that came out of the Electromagnets quiz that we did last week. So let's take a look at what those things are. So generally speaking, this first one, absolutely fine. We know that moving uh, charged particles are what actually creates magnetic fields. A few people only got 1 out of 2 here because they didn't specify that it was moving charged particles, or they started going off about some stuff about electrons and whatever. Nice and simple, moving charged particles. So next question caused quite a bit of bother. So if conventional current is flowing into the page, we need to look at how the direction would be and like of the field lines and what shape they take. So let's actually take a look at some diagrams. So if we take a look at here, so to work out the direction of the field lines, we need to use Maxwell's right-hand grip rule. So basically, you take your right hand and you make a thumbs up, and your thumb points in the direction of conventional current. So on the left, you can see there's a diagram with conventional current going into the page. That's what the X means. So you point your thumb straight at the X, perpendicular to the screen, and you should see that your fingers are pointing around in a clockwise direction as long as you made your thumbs up with your hand. So your thumb points direction of conventional current, your fingers will tell you direction of the field. So your fingers are the same direction as those arrows. If the conventional current is out of the page, your thumb will be pointing back towards you, and your fingers will now be pointing in the anti-clockwise direction. So that's how we figure out the field. But in both cases, you can see we've got these circular paths. So if we go back to the question, we've got current flowing into the page. So that's the one on the left. So we can see we've got clockwise arrows here, and they're going round in circular paths. So inside a solenoid, so we're looking at describing the field inside a solenoid, so let's do that. So this is what our field looks like. So you can see inside this solenoid here, you can see we've got lots of equally spaced field lines here. And equally spaced field lines means the field is the same strength everywhere. So the field line spacing is the same, which means the magnetic field is the same strength everywhere inside. And we can use this for all kinds of things. We can use this to turn magnetic materials into magnets, that kind of thing. But essentially, it's the same strength everywhere. Outside the solenoid, we can see the spacing between field lines is increasing. They're getting further apart. And what that means is that they are getting weaker. So the field spacing is increasing, but the magnetic field strength is decreasing. The field is getting weaker, and the further away from the solenoid you get, the weaker and weaker that field is going to get until it's basically zero. So if you're looking at solenoid from one end, you'll see conventional current traveling clockwise. So that is if we were looking from the right-hand side. So you can see the current is going in here and then going round in a spiral, but it's always going clockwise if we're viewing from the right-hand end. And if we're seeing current going clockwise, I always use these letters to help me remember it here, we are at a south pole end. And if we see the current going anti-clockwise, so again, I use the letters to help me that one, which is what we'd see if we looked from the left-hand end, we'd see the current going around an anti-clockwise. That's telling us we're at a north pole end. Another clue about the poles is the direction of these arrows. So remember, field line arrows always go from north to south. So you can see we would have known that that was a north and a left and a south and the right as well there. So if we return to our question, if we see conventional current going clockwise, you can see that's our south pole. Whereas if you see it going anti-clockwise, we're at the north pole of our electromagnet. So how could we practically determine the direction of the magnetic field? Most people are on the right track here. So we would use a plotting compass, or just compass is absolutely fine. And the field line direction is determined by the north arm or hand or pointer, whatever you like there. And so we need to be specific and actually say, because if you know what a compass looks like, so let's actually get one of those up. It's probably going to come up with something horrific. So compasses have two ends. So we need the red one, or the one that points towards north here. So That's why we need to be specific here, and actually we need to know which the north arm is pointing towards. That tells us our field line direction. So increasing the strength of our electromagnet, this one was generally fine. We could increase the current or potential difference, because by increasing the potential difference, that has the effect of increasing the current. But it's actually this one that makes the magnetic field stronger, a larger current, more turns or coils. So this one only applies if we've actually turned it into a coil, but if we have more turns, of course, and being specific, we should say more turns inside the same length there. And then a final insert soft mag magnetic material into coil, e.g. iron. So iron is an example of that. It's the one that's typically used, but that's the 3 ways we can make our electromagnet stronger. Okay, so describe how the direction of the magnetic field around an electromagnet can be reversed, essentially change current direction or change charged particle direction there. And then final one, this was generally fine apart from this last one, so we'll take a look at that. So I've got myself a sketch of this so we can add some details to it. So the first thing we need to do is label the north and south pole for the magnetic field on the left. And we know that magnetic field lines always go from north to south. So that's how I'm able to put a north here and a south here. That's what I'm doing there. On this middle one, we know the direction of conventional current because we can see the arrows going clockwise around. So using my right hand grip rule, to get my fingers pointing clockwise, my thumb is pointing into the page. So that's what tells us the conventional current is going to the page, and typically an X indicates that current is going into the page. And then, okay, this last part, we had all sorts of answers for the direction of the force. The force is always from the high field line density to low. So you can see the high field line density is up here at the top. The low is down here at the bottom. That's because the fields have added together up here, which is why we've got more field lines. They've cancelled each other down here, and that has had the effect of that will then produce a force. So this wire here will experience a force which throws it out of the field, and it will throw it down this way here. And that's something we call the motor effect, which we will look at in more depth in the next video.